that is polymer models that interact to an interface where the price or the reward does not depend on the site. And starting from today, as we have seen this morning, we consider rather disordered models. That is, models where the interaction depends on a sequence of random variables. So there are two random ingredients in the game. I have recalled here the basic definition you have seen this morning. So actually, I don't write anymore the definition of the model. I directly write the partition function. And from that, you can immediately guess what the model is. So our partition function depends on two real parameters, beta and omega, and the sequence beta and h, and the sequence of omega. And it is the expected value over S of this functional. This functional is essentially okay, I should probably say that S is a Markov chain on some space which contains a marked point, which we call star. You could think, as yesterday, to a random walk on Z, and the star point is just 0. And so what we are doing is just to modify the law of the walk by penalizing or rewarding the times at which the walk touches this preferred point. However, we reward in a disordered way. So each time S touches star, it gets a reward which is beta omega I minus h, where omega is is a typical realization, if you want, of an IID sequence of random variables. So the idea is you choose the omega at the beginning, you just throw them as a realization of this sequence, then you froze them, and you study this model where you average over S. So omega is a sequence which is fixed, it's given. So this is our model, and as yesterday, it turns out to be more convenient to look at the constraint case where we just restrict to the trajectory that come back at the end, but this is just a minor change. So this is the polymer, whose law is P, and this is the environment whose law is blackboard P. I will denote, okay, there is some slight changes of notation with respect to yesterday. I will denote by capital T instead of tau the return. This, I will stick to the notation of the paper by Frank and Dimitris Cheliotis, where this approach has been carried out. So there will be some slight change, but nothing special. So this is our model. I recall you, okay, I will not use it, but Rn, which is the law of the first return. And we are asking that essentially the decay is roughly 1 constant or something more general by n1 plus a, with a between 0 and infinity, where this rough is more general than yesterday, but I will not need it, so just to keep in mind. Now, we are interested in the free energy as usual. So the free energy, recall, is just f beta h, the limit as n goes to infinity of 1 over n log of zn constrained beta h omega. And note that there is no omega anymore on the left-hand side because, as we have proven, as Nicolas has proven in the first tutorial, this limit is almost sure in omega and it is non-random. So we have a quantity, f beta, and for this model, the interesting question is to ask whether this limit is strictly positive or 0. So there is a localized region, which is the set of beta h for which the free energy is strictly positive, and the delocalized region, which is beta h for which the free energy is 0. And by monotonicity and convexity properties of F, these regions are separated by a critical line. So there is a fundamental object, the critical line, which Frank has discussed a lot this morning. Okay, is the list H for which we are delocalized. And our purpose today will be look more closely at this quantity, which separates the localized and delocalized region. Now, the first part of this tutorial will be just manipulate slightly the partition function to get to a rather simple and direct expression for the critical line directly, because this is somewhat not too explicit definition, just the list H for which something happens. So we'll get to a more explicit expression, and then we will just make a jump to large deviation to understand how to deal with such an expression with the help of large deviation. So first part, we start from what we saw yesterday, namely we decompose the partition function according to the return to 0. So beta h omega, well, I change slightly the notation. So capital N is the number of return to 0 before small n, and then we sum over the location, which instead of t I will call k. So 0 is k0, then k1 is the time at which the walk comes back for the first time, and kn, capital N, for the last time, which must be small n since we work under this constraint. And then once we have this, we have just this product of E beta omega ki minus 1 minus h times r of ki minus ki minus 1. Actually, it's the same expression as yesterday. The only difference is that, okay, what you get is not constant, but depends on I. Now, what we do, however, now is to introduce a generating function. We have seen a lot of generating function this week. So we define g of z, small z, as sum over natural numbers zn, capital Z n c of beta h omega. Okay? Why we do so? Well, you should guess by now that since we want to understand what is the exponential rate of growth of z, well, this amounts to ask what is the radius of convergence of this series. However, in this case, it's quite simple, because if we multiply zn here, then by the same trick we have seen yesterday, well, this you can obtain just by putting z ki minus 1 here. Okay? Because you have a product, and then the product becomes a sum in the exponential, and the sum is telescoping, and the last term is exactly n. Now, this is nice, because since we want to sum over small n, now look, small n in the right-hand side appears only here, in no other place. It's just a constraint on the last point being n. So, if we sum over all possible n, the right-hand side, we just get the right-hand side with no constraint on this, except being finite. So, very simple, g of z is just, we sum, this disappears, so we get sum n in natural number of this sum, where this time I just require a kn to be strictly increasing, but I don't condition anymore the last time. And then, okay, I slightly modify this. I put r of ki minus 1. And then I prefer to write this as the exponential of the sum for I equal 1 to n of beta omega ki minus 1 minus h plus log z ki minus ki minus 1. Okay? Now, all this expression let me call it Fn, F capital N, which depends on beta, H, omega, and also Z. And what is this expression, actually? It's a sort of, okay, let's write it slightly differently. Now, this sum and this product just amounts to average over the first capital N returns of the random walks. So this is just, by definition, just elementary probability, the expected value of the returns of the random walk of this function. So we have the exponential sum for I equal 1 to capital N of beta omega t I minus 1. Recall that capital T is the first return, minus H plus log Z Ti minus Ti minus 1. Okay? So, what is this kind of function? Well, essentially, it is a sort of partition function where instead of having a polymer of a fixed length, small n, you have a polymer where you fix capital N, which is the number of return to 0. So it's a polymer for variable length constrained to have exactly capital N returns to 0. But why this is interesting? Well, first of all, let me state it explicitly that the radius of convergence of G is Z critical, which is E to the minus the free energy. Why this? Okay, by definition of the free energy, because this is exponential of n times the free energy plus small o of n. Okay? So the z at which this diverges is exactly e to the minus free energy. So, you see, to understand whether, recall our problem is to understand what is H critical. H critical is the point at which the free energy becomes positive. So deciding whether the free energy is positive or 0 amounts to asking whether the critical point is 1 or it is strictly, the radius of convergence, sorry, is 1 or it is strictly less than 1. So we just have to ask, does this series converge for every z until 1 or it starts diverging strictly before 1? So the idea is, well, this series we have is just the sum of Fn. Then, well, naively say, take z very close to 1 and ask if this series Fn is summable or not. So we have just rephrased. But this is nice because the H now appears in a very simple way. We can just pull it out because it's H times N. Okay? So more precisely, we can rewrite this as the exponential of n times Sn beta omega z minus h. H times n is what is here, and Sn is all the rest. Sn is the one thing that makes this is an inequality. So is 1 over n logarithm expected value. You have seen a lot of times this kind of expression. Sum for I equal 1, 0 to, no, okay, 1 to n of beta omega t I minus 1 plus log z ti minus ti minus 1. Okay? Now, why do I write this way? Because it's actually quite easy to see that by subadditivity argument, Sn has a limit as n goes to infinity. So Sn will converge to some limit S of beta and z. So since we are just asking whether the sum of these converges or diverges, well, it's clear that you have just to decide whether H is smaller or less than S, because we have En times this, so it's an exponential increasing or decreasing sequence. So finally, I spare you some details. Since we are interested in Z, which must go to 1 from below, I hope to give you an idea. We can actually neglect this term. Log Z becomes 0. This requires some justification. But finally, what I want to tell you is that to decide whether this converges or diverges is just looking at S of beta, which is the limit as n goes to infinity of 1 over n logarithm of this quite simple expression, at least 1 over n omega ti ti minus 1. And if h is bigger than this S of beta, this series will converge for Z arbitrarily close to 1. Otherwise not. But then this means that this S of beta is nothing but the critical curve. So I've been slightly quick in the last step. So I apologize, but this, okay, the steps that are required to make this precise are really not very difficult. So what we have got is an expression, an explicit expression for the critical line. The critical line is this rate of exponential growth for this quantity. Now this quantity has a nice interpretation. Recall, omega is a sequence, a quenched sequence of random variables, IID, and then you run your Markov chain, which has returns, and you're asking, well, you would like to find, you know, the strategy of placing the returns in order to maximize, in a sense, this price that you get. So, and this limit is the critical value. So now we are happy because we have an expression for the critical value. However, this is not so explicit. The point that Frank was discussing this morning is that with the help of large deviations theory, one can give an explicit, though quite abstract, expression for this limit. However, in order to discuss this, I have to introduce some large deviations notation. And since I think that not everybody is familiar with the, okay, there is, with that, now we make a pause, so we forget for the moment our polymer, we just keep this expression, and we will talk about large deviation for a while. Now, I hope that people that already know large deviations don't get bored, and that people that do not know may understand something. So actually the introduction will be really very specialized to what we are interested in. The focus of our presentation of large deviations would be actually Sanov theorem. But in order to discuss it, I need first a very brief presentation of introduction of relative entropy. Probably some of you have already met relative entropy, but let us discuss briefly. So we have a measurable space, gamma G, and we denote by M1 of gamma the space of probability measures. On gamma G. Now, if we are given two probabilities, mu and rho, which are in M1, we define a quantity which is called the relative entropy, in this way, the relative entropy between nu and rho is, well, we have to distinguish two cases. Either nu is absolutely continuous with respect to rho, okay, or not. Well, if not, then it's easy. It's prime infinity. If nu is not absolutely continuous with respect to rho. Okay? If I recall you that, okay, nu is absolutely continuous if it's given times a function, okay, the integrals, okay, it's a density times rho, and the density is called d nu divided by d rho. And then, otherwise, if it is absolutely continuous, it is defined as the integral over gamma over of d nu over d rho log of d nu over d rho in d rho. And actually, I prefer to write it this way, but you see that since you can, in a sense, simplify, and you can write this as the integral over gamma of log d nu in d rho with respect to the measure d nu. And it's the same. However, I prefer to write it this way because then this you can write as a function g of d nu over d rho, where g of x is just x log x, and 0 if x is 0. Okay? Now, the point is that if you write this way, you see it's easy to see that g is a convex function, is bounded from below, so this integral always makes sense. But not only this. By convexity, just using Jensen inequality, easy exercise, you derive these basic properties that h of nu given rho is always greater or equal than 0, Jensen exercise, and it is 0 if and only if nu is equal to rho. So there will be a lot of things to say about relative entropy, but for the moment I just would like you to look at this as a way to quantify how nu is different from rho. Okay, it's not the only way. Beware, this is not a distance. It's not symmetric, does not satisfy triangle inequality, so it's not a distance. However, it's a way of quantifying the difference between nu and rho. And this will turn out to be very useful in a moment. Okay, just in a very special case, now we focus on a very special case. If gamma is finite set, so say gamma is 1 R, we can identify, then of course measure on this set are just R repels, so just R real numbers that add up to 1. Then in this case, h of nu given rho is just the sum for I equal 1 to R over nu I logarithm of rho I divided by, no, sorry, nu I divided by rho I. So it's a very simple explicit expression. It's a convex function, actually. This is always a convex function of the probability. However, this is just all I want to say about relative entropy. This is because they enter in large deviations for what we want to talk about, that is Sanov's theorem. What is Sanov's theorem? It's a beautiful theorem which describes the behavior of the empirical measure associated to a sequence of random variables. So we start with the finite case, which is the simplest. So we have a finite space, gamma, as before, 1 R, and then we have a sequence of random variables that take value, say IID, in gamma. And rho, say, is the law of the marginal law of the sequence. Okay, it's a law on gamma, and we assume that it is strictly positive on every element. Otherwise, we could just erase the elements. So rho I is strictly positive for every I from 1 to R. Now, there's a lot of things you can do with this sequence, but for us, it will be important to consider what is called the empirical measure. The empirical measure is this thing. You just take 1 over n, sum for I equal 1 to n, delta at yi. What do I mean by this? Say fix omega, and this is the Dirac mass at some point. So Dirac mass is a probability. You make a sum of n probabilities, you divide by n, you get a probability. This is a random probability, okay? Random probability on gamma. That is, it's a random variable taking values in the space of probability measure on gamma. Now, in general, it's quite, these are in general abstract things, but this is very simple because it's a finite set, so the probabilities on gamma is a very simple set. It's just the set of real numbers. Positive are real numbers such that they sum up to 1. So essentially, it's a subset of the Euclidean space. So it has the Euclidean topology. It's something we know very well. So in a sense, you could just think a subset. It takes value in R to the power R. Now, what is the nice thing? It's a very easy exercise to show that by the strong law of large numbers, we have the almost sure convergence of this object. First thing, exercise. Almost surely, the limit as n goes to infinity of Ln is equal to rho. Rho is the law of y1. Look, this convergence takes place in M1. Okay, we have a random object taking value in this space, which almost surely converge to a limit point of this space. Now, this is not. This is quite intuitive, just an application of the law of large numbers for independent random variables. And just to be clear, Ln is a random measure, and what is the value on I is just 1 over n sum, okay, on j for I equal 1 to n, indicator function yi equals j. So is the fraction of times that the sequence until n takes the value of j. So it keeps track on how many, the relative frequencies of each values. Now, what is large deviations about? Large deviations is an attempt to, in this context, to answer the question, what is the probability that Ln takes a value which is different from its limit for large n? Because this law of large numbers tells you that with high probability, Ln will be close to rho. Rho is the law of y1. However, now, let us take a different, say, probability. And we ask, what is the probability that this random probability, instead of being close to rho, is close to nu? Now, we should be more precise about what means close to, but in this context, it's quite easy because the space we are living in is just Euclidean space. However, to be more precise, I leave you another exercise. Every exercise is written here. You can really do if you want. They're not difficult exercise. Let we take a special nu in this form, ki over n, where k1, kn is a factor of natural numbers, okay, R, that sum up to n. Well, then it's easy. I mean, it's easy. Then you can really compute the probability that Ln is equal to this kind of nu. Look that this is the values that can be attained by Ln, since Ln are fraction of numbers, so they cannot be irrational, for instance. But, well, this, I just write you for, okay? Just a multinomial expression, which doesn't tell you a lot. However, the interesting thing is that if now you replace the factorial by Stirling's approximation, then you discover, this is an exercise again, then this expression for large n is equal to E minus n times the relative entropy between nu and rho plus correction terms that are small o of n. So here you see the relative entropy come out. What's happening is that if you ask your empirical measure to be close to nu instead of rho, since rho is not its limit, this probability will decay to 0. And the nice thing is that it decays exponentially fast. And the rate of exponential decay is precisely given by the relative entropy between nu and rho. So, in a sense, this is the idea behind large deviations. Now, this is a very specific computation. You can make it because this is a value that can be attained by Ln. However, you can generalize this in a much more broader sense in this way. For every O open set of M1 of gamma, for every C closed set of M1 of gamma, then you have this relation. If you take the probability that Ln belongs to an open set, and then you look at the rate of exponential decrease, you get as a limit minus the infimum, you have to take the inferior limit, and then you get that this is greater than or equal to the infimum over nu in the set of I of nu, where I of nu is exactly the relative entropy. And the superior limit of the same thing, the probability that the empirical measure belongs to a closed set, is less than or equal to minus the infimum over the closed set of the same functional, the relative entropy. Now I write this relation because these relations, which are less explicit than this, however, are much more general. So in a sense, since you have a random variable, usually random variables don't take discrete values. You cannot ask what the probability that the random variable takes some single value. However, you can ask the probability that the random variable takes values in some set. Well, what you can prove is these two inequalities, which are very interesting. You should think of them as taking O and C very close to some specific value. Then, if the function I is regular, then this will be not very far from I on the center of this set. So, this is a brief excursion, but beyond these technicalities, you should think that the idea is that in this situation, you have a function which quantifies the probability that your random variable takes a different value from what it should take. Now, this is until now, okay, let me close saying that when these kind of things happen, we say that Ln satisfies a large deviations principle with rate function I. Okay, so hoping that I have not completely destroyed your attention. Now, what you should remember in general, beyond the case of Sanov theorem in finite space where everything can be easily proven, is that we had this IID sequence of random variables. We consider the empirical measure that keeps track of the relative frequencies at which these variables take their values. Then we have that the empirical measure almost surely converges to the marginal law of the sequence. And if you ask what is the probability that the empirical measure takes instead a different value, then this decays exponentially with rate function given by the relative entropy. Now, I have done this only in the finite case, but now some leap of imaginations are required. First of all, you should not have difficulties or surprises if I tell you that everything can be extended from the finite case to much more general settings. So, first extension is let gamma, instead of a finite space, just a Polish space. What is a Polish space? A complete separable metric space. Then, well, you can always take Yn, an IID sequence in gamma. Whenever you have a metric space, you always have a natural sigma field, sigma algebra on that, the Borel sigma field, the one generated by open sets. So you can talk about probabilities there. So we take an IID sequence in gamma, and with marginal law rho, y1. And then you can always define in the very same way Ln, no difference. The empirical law, the empirical measure of the first n random variables. This is a random law, except that this time the space of probability measure is no longer a simple space. This is always probability. Well, you should define a notion of convergence here. It is the weak convergence. You should probably have met it, but I don't want to go into details. What I want to tell you is that almost surely you always have that this empirical law converges to rho, the marginal law of the sequence. Almost surely. And this convergence takes place in the space of probability measure. For this you need to define, but just this is not very important. Now, what happens is that, again, Ln satisfies a large deviations principle. What does it mean? Exactly, with no change, what I wrote here. If you take any open set of the space, any closed set, this relation holds. With I, the relative entropy. So really no difference. What you should think of is that the probability that Ln is close to a different law, nu, instead of the marginal rho, well, this decays exponentially fast with rate I of nu, where I of nu is just the relative entropy. So this is the first generalization, which should not be too surprising or too difficult to grasp. The second generalization, on the other hand, will be really some leap of faith, and then will be to pass from keeping track of single variables to keeping track to words. So if you think that these are the letters of our alphabet, you want to keep track of words. So second generalization, well, if you fix L, then you could define ln L in this way, 1 over n, a sort of empirical measure, but you just keep track of y1, sorry, yi, yi plus 1, yi plus L minus 1. So instead of just looking at the single variables, you just take L consecutive variables, and you look at the statistics of these L consecutive variables, where we put periodic boundary condition for simplicity. Okay? This is just a minor stuff. Now, what kind of object is this? This is a random probability, but not on gamma to the power L. So this is a random variable taking values in the probability measures of gamma to the power L. Then you could show that ln L converges as n goes to infinity to, well, not very difficult to imagine. Since the variables are independent, the statistics of consecutive variables should be more or less independent, and almost surely this converges to the the product measure L times of the marginal law itself. And again, you have large deviations. I will not write it more precisely, because we still need a last leap of faith. So we have passed from a single letter to a word of L letters. Well, we need more than that. We need to count words of arbitrary length. So maybe now you can imagine what you are going to do. You are just taking the whole sequence of n letters and then just rotate. So finally, and this is really finally, what we are going to do is now define y1, yn periodized as the infinite sequence which is obtained repeating periodically this. This is just a notation. This is just y1, y2, yn, y1, y2, yn, y1, etc. Now, if you take this sequence, this is an element of gamma to the n this time. And you define the shift from gamma to the n to gamma to the n, that to a sequence y, y1, y2, etc., associates y2, y3, etc. Now, then you could define what is called the empirical process Rn, which is just 1 over n, sum for I equal 1 to n, delta of theta I of the sequence periodized. This strange object is a range of objects which takes values in the probability measure on the space of infinite sequence. and not only probability measure, but probability measure that are shift invariant. So this is a very abstract object. I don't expect you to just have a clear idea of what it is just by the definition. Try to think. But it's a way to look at the statistic of words of arbitrary length. Now, again, you can show that Rn converges almost surely as n goes to infinity to the law, which is just the infinite product of the marginal laws on this space. It's very strange thing. And finally, that, again, a large deviations principle holds. Well, with rate function, okay, which is the, okay, is a very complicated rate function. You don't think, I mean, it's just the relative entropy, but you have to pass to a limit. I don't want to write it in detail. Now, why are we doing all this kind of quite complicated stuff? Because it's time to come back to the polymer model, and in particular to the sequence of letters which are read, of words which are read by the polymer. So I recall you, this is T1, this is T2, this is T3, etc. And here we have omega 1, omega 2, etc., omega T1. Now, as Frank introduced this morning, we have associated a sequence of words. Yi is just, let me note, the word omega ti minus 1, omega ti minus 1 plus 1, until omega ti minus 1, which is just, this is y1, the word read from the first excursion. This is y2. These are words in the environment. Now, since the environment is an IID sequence, okay, the omegas are IID, and the polymer is a Markov chain which is independent, it's easy to realize that this sequence of objects, which takes place in the complicated space R tilde, which is the union, okay, each yi takes values in a finite union of R, so R to the n for some n, is an IID sequence. Okay? Is this IID if we average both on the disorder omega and on the walk? So, by what I told you before, if you take Rn, which is exactly what I wrote here, the empirical process, okay, corresponding to this sequence of random variables, which are slightly complicated one, well, it satisfies a large deviations principle. So it has a limit, and we can quantify the deviations from the limit. Now, the point is that all the theory I've just told you is quite classic, you can find in any book of large deviations, and it is because this sequence is IID. However, the interesting point is that, in our case, we would like to make the analysis not averaging both on omega and S, but only on S. So we would like to fix a typical sequence of omega and average only on S, on the excursion of the Markov chain. So in this case, well, you can, in any case, define the same quantity. The empirical process. But now, let me write omega here, because I want to say that omega is fixed, and I'm just looking at this object under the probability given by the excursions. Now, this is a much more difficult object. However, as Frank pointed out, you can still prove that Rn satisfies a large deviations principle, namely that the probability, this time only under the random walk that Rn omega is close to some law nu, decay exponentially, okay, let's call Q the law, minus I of Q, where I of Q times n, where I of Q is an explicit function. Now, what is the link with what we did before? What we did before is that if we average both on P and on blackboard P, well, in this case, the decay is given by, this is E quenched, this is called the annealed, is exactly given by, well, an extension of the relative entropies given before. In the quenched case, when we average only on that, it's a different function, and it is strictly greater than that, because it's more difficult to observe deviations. Now, I hope that at least well, with this very, very crash introduction, very brief introduction, you have a rough idea of, I mean, what does it mean when we write these things, at least very roughly. And now, in the last, they say, 8 minutes, well, let's come back and see what does this have to do to this problem. Well, the point is, to come back to this problem, is that the quantity we are after is a very difficult quantity, but it is a function of our object. What are we doing here? We are taking the omega at the times ti minus 1. Of course, actually, let me write here. One over n, I equal 1 to n, omega ti, which is exactly the expression which appears here, is a function of our, capital N, omega, random process. That is, if you know all the statistics of the first n words, of course, you can, in particular, extract in an easy way, just take the statistics, the mean of the first letter of every word. Okay? I write this phi in general, but it's easy to write it. Now, in this case, the expression that we have here, we can write as expected value of exponential of n times a function of r n of omega. This is a simple equality, but it's a very abstract one. We have a very concrete quantity, and we are expressing it as a function of a very complicated object. Why do we do so? Because whenever you have a sequence of random variables which satisfy a large deviations principle, then you have an important result, which is called Vardan's lemma, which allows you exactly to compute the asymptotic behavior of this kind of functionals. So what I'm just going to explain you, I don't see any more stuff to erase, it's there, is that okay, I forgot a beta. Okay, so there is a beta here. Is that Rn satisfy a large deviations principle with rate I, then 1 over n log the exponential of the exponential of n phi of Rn has a limit, and the limit is quite simple to write. Is the sup over q of beta phi of q minus I of q. Why does this happen? This is a general result, but I want to conclude in the last 5 minutes just to give you a hint. The reason it's quite simple, actually, if you look at it in a very, very special case. Imagine so Rn is a very complicated object, takes value in a huge space, a space of probability measure on infinite sequence. But let us pretend that Rn take value in a finite space. We call it E. Well, no, it's not a good, okay, gamma. Then, what is the expected value of E to the beta n phi or Rn omega? Well, we just have to sum over all the value in the space of E to the beta n phi of x times the probability that Rn is equal to x. However, if we have a large deviations principle, this probability is approximately E minus n I of x. We are just told this happens. But then we are done. You see, we have simply the sum over x in the space E of E to the n times beta phi of x minus I of x. And you want to understand what is the asymptotic behavior of this as n goes to infinity. Well, you have immediately a lower bound. You take the x that maximize the exponent. So this is greater than E n the supremum over x of beta phi of x minus I of x. Okay? On the other hand, you have an upper bound. Since the space is finite, cardinality of E times the same thing, E to the n supremum over x of beta phi of x minus I of x. So you see, whenever you have a sum of exponential, the leading one, the one with the greatest rate wins. You take 1 over n logarithm, this does not count, and you get this. So what is the moral of everything? This is a rough computation made on a finite space, but what large deviation theory tells you is that if the function phi is sufficiently regular, continuous and bounded, say, and if the variables Rn no longer take value in a finite set, but in a general set, but satisfy large deviations principle, which basically tells you that this holds in a precise sense, well, this result still holds true. So if you have, just to remember something, is that you have some relatively concrete quantity that you can express as the expectation of the exponential of n times a continuous functional of some random variables, some sequence of random variables which satisfy a large deviations principle on some space. And then there is a very powerful theory which tells you that you can deal with this expression. I know it's been a lot of material in this tutorial, but if you want to just look more closely at this kind of notions, Frank has written a very nice book on large deviation, a very short one. You can find basic things. Otherwise, there is a beautiful book by Amir Dembo and Ofer Zaitouni. And if you want to look more closely at what happens after these preliminary steps, just look at the paper Frank has written, and it's on the archive. So thanks, and we're done.